Hi, everyone. Welcome back to E54. Today, we're going to jump into lecture 11. So up to this point, we've been building up a lot of the tools we need to know to understand material science, talking about microstructure, phase diagrams, phase transformations, defects, all these kind of things. But a lot of the examples we've been giving have been in metallic systems. So today, we're going to start to spread our wings a little bit and talk more about ceramic systems, okay? So some of the primary issues that we're going to address are: what are the crystal structures and how do they differ from what we saw in metals? What do point defects look like in ceramics? How are impurities accommodated? What do phase diagrams look like? We'll see that a lot of these things are similar. And then we'll finish with mechanical properties of ceramics and how they differ from metallic systems. So just to go back to some of our examples that we saw at the very beginning of class, one of the materials I mentioned was quartz. This is a crystalline silicon 2-oxygen compound, right? The base unit is shown here at the top left. We can start to pack these together, form the crystal structure. And then if we put many of them together, we can start to get a crystal that looks like this, right? And this is reminiscent of real quartz crystals we see in sort of nature. And this is just showing that that faceted structure that you can find is connected to that crystal structure. Okay, so one thing we have to do is start going back and thinking about atomic bonding again. So in metals, we had it easy. We just talked about metallic bonding and sort of forgot about what we were thinking different options are. But for ceramics, we can have either ionic or covalent character of the bonding. And the way we can determine which one we get is that the percent ionic character is generally going to increase with difference in electronegativity. So if you remember back to one of our earlier lectures, we said elements with different electronegativities fall on different sides of the periodic table. So for example, calcium and fluorine going together to make calcium fluoride, those are going to have a large electronegativity difference. And the bonding is going to be 89% ionic, right? To compare that or contrast against that, we can take something that's close on this periodic table. So we'll take silicon and carbon to make silicon carbide. And here we find that only 12% of it is ionic character. Okay. So we want to start jumping into thinking about crystal structures. And one of the first things we can talk about is how the relative size of the ions will affect and control our crystal structure, okay? So one thing we have to remember is that when we make a ceramic, we're putting together charged ions. Some have a positive charge, some have a negative. And often what we want to do is maximize the number of oppositely charged ion neighbors, okay? So if we just think about this little positive ion here, it wants to be surrounded by 4 negative ions whenever it can. And this is the first place that the size of the ions comes into play. So for these two examples on the right, we'll start with this middle one. So this is the case when that negative ion is just the perfect right size to fit into the gap between the larger negative green ions here. So if it's exactly that size or larger, what's really important here is that always this blue positive ion is surrounded by 4 negative guys. In contrast, if the ion is too small, so it's tiny, it's smaller than that gap, there's going to be some variation. If I look at a given point in time, I might only be close to 1 of those ions, or maybe 2, or something like that. But the point is it's not consistent, and we're not sort of optimizing how we're filling that space. So these 2 on the right are stable configurations. This one on the left is unstable. Now, the other thing we really have to think about is we have to maintain charge neutrality. So the ions themselves will have positive or negative charges, but overall, our material wants to have a net neutral or 0 charge. Okay. And a good example of this is calcium fluoride. So calcium by itself is a 2+ cation. Fluorine is a -1 anion. So that means that for every calcium atom, we need to have 2 fluorines. And that's usually reflected in the chemical formula. So calcium, fluorine 2, That's just telling us that we have that ratio between those atomic species. So if we start to build up this understanding, what we can start to do is look at things like the ratio between the cation and anion radius, and notice that generally the coordination number increases as this ratio goes up. So on this table right here, what it's showing is on the left column is the ratio of the cation to anion ratio. And you can start to, as we go down this, it's getting higher and higher. Okay, so 1 is the top, so that's when they're the same size. Other times the anions are smaller. Sorry, the cations are smaller. I apologize. But as we go down this table, the coordination number increases, and you can also see some graphical representations of how the atoms are going to be organized, right? So if we had a really small cation, the optimal way to organize it would be in this linear type of trend. If it gets a little bigger, we can have it be in a triangular format. Gets a little bigger still, it can be in a tetragonal. So it's basically, this is a 3-dimensional piece. There's 3 atoms in the bottom plane, 1 atom stuck on top. And then in the space in between is a cation. If you want to see this, we can look at this call out, this 3-dimensional picture of this, where we can see there's that tetragonal shaped site for that blue cation. Keep getting larger and larger. Octahedral is the preferred site. You can see again on this 3D example, this blue cation here, it's surrounded by 4 anions in the plane, and then 1 above and 1 below. And finally, we can even have a cubic type of stacking. So this blue one is in the center of a cube with green ions all at the corner. Okay, so these 3 examples, which are helpful for visualizing this, are actually also very well-known examples of ceramic materials. So zinc and sulfur is something called a zinc blende structure. Sodium chloride is so common that we actually call its structure a sodium chloride structure. And the same thing with cesium chloride. We actually name the structure after this material. And we're going to come through and come back to these structures a little bit. So don't worry if they don't seem totally sort of natural yet. Okay, so let's start to work through an example of this. So let's think about asking ourselves what the minimum ratio of cation radius to anion radius could be for an octahedral site. We mentioned that the minimum size we would want is something that's just barely touching all of the atoms around it. Okay, so this is in that plane. So there's the 4 atoms around it. Remember, there's 1 atom on top and there's 1 on the bottom. We're just not showing those right here. We're just showing the dashed line, dashed circle so that we can see. So we can think about what that would be, and we can acknowledge that 2 times that radius would have to be equal to square root of 2 times A, where A is the side length. So we're just doing some geometry, noticing that it's a right triangle. We know the length of this side A, and we're trying to calculate what that side is. So we can plug in the fact that we know that that's 2 times the radius of the anion. Go through and solve, skip to the end. So this is actually 0.414 is the minimum cation to anion radius for this octahedral site. This was that lowest value that we had in this table right here. Okay, so that's the minimum, and it can be a little bit larger than that. The next minimum we're going to calculate, it would be for the cubic site. Okay. We won't spend our time doing it here, but that's what you would do. Okay, so we can go and think about how this applies to different materials. Let's look at the sodium chloride, which is also sometimes called rock salt structure. This is in an octahedral site. This actually looks like 2 different face-centered cubic lattices that are interpenetrating. So if you sort of block out the orange or red atoms for now and just look at the green ones, you see that there's atoms on the corner and then atoms in the center of all the faces. Okay. The red atoms are on a similar type of lattice, but it's just shifted over half a unit cell. So if you imagine a face goes right here, there would be atoms on all the corners and one on the center of that face. Okay. All right, but getting back to the relative size, we can go and look up what the ionic radii are. We can take that ratio, and this is going to be 0.564. And that would be from our table where we read that we would want octahedral sites, and sure enough, that's the type of site they form. So this guy has 4 ions in the plane, 1 above and 1 below. We could go and do this if I were just to give you a random ceramic. So for example, if I said, hey, iron oxide, what would this want to form? We could go and recognize first that iron is going to be the cation, oxygen is going to be the anion. You can see that 2 plus and 2 minus, so it means it'll be 1 to 1. Take that ratio, 0.55, and again, we're going to be in that range where we would predict an octahedral site. So between 0.414 and 0.732, and we'll have that sodium chloride type structure. You could keep doing this, lots of other systems it works for. This is just showing you another example. So magnesium oxide is a similar system. Take the ratio of the radii, it falls in that range. And if you look at the structure of magnesium oxide, it again forms that sodium chloride or rock salt structure. There are some other ways of describing these structures. Sometimes you will see ceramics described in terms of their chemical formula. So these ones we just talked about, sodium chloride, iron oxide, magnesium oxide, are all what we would call AX crystal structures. And all that means is it's just a 1-to-1 ratio. So 1 sodium for 1 chloride, 1 cesium for 1 chloride, 1 zinc for 1 sulfur in this, okay? What I want to point out real quickly is this way of describing it is only talking about the chemical formula. It's not necessarily talking about the types of sites that are filled, okay? The way you can see this is we talked about sodium chloride having those octahedral sites. Cesium chloride is shown on this slide. So even though it's a 1-to-1 ratio, it has a different crystal structure. If we go and we take those ratios, we find that it's 0.939. So that's larger. And that would sit in the range of cubic sites from that table. So it's going to look like a simple cubic with a cesium atom in the center. Okay. So the point is that this crystal structure, you can't just look at that 1-to-1 ratio and pick out what the crystal structure is. Okay. So there's sort of multiple pieces to this puzzle. Zinc blend is the other crystal structure I mentioned. So this is also good for pointing out that although those ratios of the ions can often predict the crystal structure, it's not a perfect system and there are times where it fails. The zinc blend is one of those. So this is a 1-to-1 mixture of zinc and sulfur. Okay. Other types of crystal structures that form this are zinc oxide, silicon carbide, things like that. Again, we're still talking about AX crystals. So this, if we went and did the ratio of the ionic radii, it's doing it for oxygen, but you could do the same thing for sulfur. It's just, I only had a picture for zinc and sulfur. What you would find is that that ratio would be 0.529, and that would predict an octahedral site. But if we look at materials that form the zinc blend structure, that's not correct. What actually happens is it looks like these yellow atoms are on a face-centered cubic lattice. And these blue atoms are filling in 2 of the possible interstitial sites. And if we look, these are surrounded by these 4 atoms, and they're going to actually be tetragonal interstitial sites. Okay. So I want to just point out that this ratio process works many times, but not always. In this case, zinc favors hybridized bonding. So the way it wants to spread out and bond with those surrounding sulfur, oxygen, or whatever atoms, it wants to do it in this tetragonal structure. So there are exceptions to those rules of thumb that we're looking at. I won't jump over to it, but I do want to point out once again that virtual material science and engineering can be a very helpful tool for visualizing this. I can only present to you two-dimensional pictures of these three-dimensional structures, but if you want, you can go in and click on many different common ceramics, and you can rotate this material around and look at it from different views. You can even pick out the different planes and see how the atoms are packed, which is very helpful. Okay, so AX are one-to-one mixtures. Of course, you can get different versions of this. So the next step up in complexity is AX2. A good example of this is calcium fluorite. Okay, so one calcium, two fluorine atoms. Other common examples are things like uranium, zirconia, ceria. So lots of different metals mixed with oxygen in this case. This right here on the top is one of the ways that calcium fluorite can arrange, and it's actually called the fluorite structure. What this looks like is it has the calcium atoms on all of the face-centered cubic sites. Okay, so corners and the faces of this cell are filled with calcium atoms. And then all of those tetragonal interstitials are filled. So in the slide before, we had just 4 of these sites filled. In this case, all of them are filled up. Okay. It's also possible to have what's called the anti-fluorite structure. So this would be if you were to switch the position of the cations and the anions. Okay. Finally, I want to mention that it is possible to have a different version of the fluorite, which has a cubic type of site. So in this case, the fluorine atoms are on the outside. And then in this case, there's 1, 2, 3, 4, 5, 6, 7, 8 cubes. And 4 of those cubes, the top back left, the front top right, the front bottom left, and the back bottom right are filled with the calcium atoms. So this is another possibility that's a little bit less common for having a fluorite structure. If we build it up even more, AX3 is what's actually called the perovskite structure. So a good example of this is barium titanate. This is a complex oxide. So it actually has the corner of these cells, barium atoms. At the faces, it has oxygen atoms. And then at the center, it has a titanium atom. Okay. So one thing we'll have to do is we'll have to calculate the density of different ceramics. And although this might seem relatively complicated, as having different mixtures of atoms being put in different places, it's actually relatively easy using all the principles we've learned so far. So the density of a ceramic can be described by this simple equation. So it's going to be equal to this n prime, which is just the number of formula units per unit cell, multiplied by some term, which is just the sum of the atomic weights in the cations and the anions in the formula unit. So this whole thing right here is just talking about that formula unit. So if it's calcium fluoride, we look at how many calcium, how many fluoride they have, and then what are their atomic weights. On the bottom, we divide by the volume of the unit cell and Avogadro's number. That's just trying to account for the fact that atomic weight is talking about how much mass per a given number of atoms. Okay, so let's do this for one of those structures we saw. So let's take that sodium chloride, just showing it, they're redrawing it here so that we can see it. So the first thing to do would be figure out what all the terms are. So the atomic weights are relatively easy to figure out. So sodium chloride, we just have to put the atomic weight of sodium, atomic weight of chloride, or chlorine, because there's only one of those in that formula. But we then need to look at this unit cell and figure out how many units are there of NaCl, right? So we can do the same thing we did before when we were talking about these crystal structures to begin with and count the number of atoms in that unit cell. So let's start with the chlorine. There's going to be 1, 2, 3, 4, 5, 6, 7, 8 corner atoms. But remember, those are shared amongst 8 cells. So there's 1 corner atom per cell. We have 1, 2, 3, 4, 5, 6 face-centered atoms. But again, those are shared between 2 cells. So that becomes 3, total of 4 chlorine atoms in this unit cell. We can do the same thing for the orange sodium atoms. Just to save time, I'll tell you it's going to end up being 4 as well. So in the 1 unit cell, we have 4 NaCl. Okay, so that N prime will be 4. The next thing we need to do is we need to figure out what the volume of that unit cell is. Okay. So in this case, the ions are drawn smaller so that we can see what's happening. If we show them at full size, we can end up seeing, we're looking along one of those front faces, so we can see where the atoms touch and how that relates to the geometry of that unit cell. So the length of one of these sides is going to be A, and we can express that in terms of the ionic radii. So it'll be 1, 2 chlorine radii and 1, 2 sodium radii. Okay. So the volume is going to be 2 times the radius of sodium, 2 times the radius of chlorine to the power of 3. Plug all these numbers in there, and what we'll end up finding is the density of sodium chloride is 2.14 grams per centimeters cubed. Okay, we can start looking at more and more complex versions of this. The next one I want to introduce is what are called silicate ceramics. And these are really important because 2 of the most common elements on Earth are silicon and oxygen. In this case, the silicon is inside of a tetrahedral site, so it's surrounded by 4 oxygens. Okay. But what's also interesting about the silica is that there's lots of different polymorphic forms we can have. So that quartz was a good example that we started with, but there's other examples too. So what's shown here on the right is what's called cristobalite. So but still, if you look closely, it still fits that structure that for every blue silicon atom, it's surrounded by 4 oxygen atoms, but it's arranged in a different way. So in this case, there's a more complex interpenetrating class. Okay. These materials are also interesting because the silicon-oxygen bond tends to be really strong, and you get high melting temperature materials. We can call a whole range of materials built on this principle silicates. They're all built around this silicon plus 4 oxygen type of structure, and then you end up putting these together in fun and interesting ways. So this is just showing how you go from 1 to 2 to 3 chunks of this. This is also demonstrating how we can start to add in other cations to balance this out. So for example, it's common to have something like calcium added to silicon and oxygen to form a different type of silicate, maintain that charge neutrality, but ionically let them still have these SiO4 units. This silica can also form a very common glass. In fact, most of the window glasses that you see out in the world are made of this. So we take that tetrahedral site, and if we put that together in a very ordered fashion, we get quartz or cristobalite or one of these other crystalline forms. But it's possible to put together these tetrahedron shapes in a way that's disordered. So in this case, this is showing what's called soda glass. So it's sodium, silicon, and oxygen. And locally, if you look at it, you're always getting those silicon and 4 oxygen units. But there's no sort of ordered lattice I can work my way around. They're put together in some random way. And in this case, this is partially accommodated by those sodium atoms being in there to balance the charge locally, but also to fill in some of the space and keep it from having an ordered structure. It's possible to get glasses with all types of other elements in addition to sodium. Things like calcium, aluminum, and boron are very common ones. That's not the only sort of option we can have. So we can have what are called layered silicates. So this is showing a two-dimensional picture. So this is connecting together these SiO4 tetrahedra just in a 2D plane. So almost like what we saw when we talked about graphene. Okay. The problem is there's a net charge with some 2D structure like this. So these layered silicates don't form just with this silicon and oxygen layer. They actually tend to be balanced by another plane of material with positively charged cations that will balance out that charge. This is a good example. It's showing this kaolinite clay. So it's a silicate layer down here. But then on top of it, it has this aluminum, oxygen, hydrogen based layer. Okay. And the idea is that this silicate layer has a negative charge. And this aluminum rich layer has a positive charge, and these balance to give them a net zero charge amongst these two layers. And you can imagine keep stacking up version of these layers on top of each other, and you can have this alternating layer inside of your structure. Now, these adjacent sheets tend to be loosely bound. So they're not having the direct ionic bonds that we get within the layers. Instead, between the layers, we tend to have van der Waals forces. Okay. And now the net effect of that is that these 2D sheets of material are very strong within the plane, but not between the planes. So you can imagine sort of shifting and shearing off these planes from each other. We often see lots of these structural features we mentioned and have discussed today in generic ceramics in the polymorphs of carbon. Okay, so diamond is one of those polymorphs that's very well known. It has tetrahedral bonding of the carbon. So if we look, there's carbon atoms on the corners and the faces of this unit cell. And then there's also some at 4 of these interstitial sites. And each of those ones is surrounded by other carbon atoms to give a tetrahedral bonding. Okay? Now this shows the power of this type of bonding. It's the hardest material known, has a very high thermal conductivity. If we get these in large single crystals, these are things you might see as gemstones or wedding rings. There's also more practical engineering applications. So we often use small diamond crystals to cut and grind other materials because they're so hard. Okay. So for example, it's not flashy, it's not a big diamond, but when my research group, we go and we take metal samples of nanocrystalline materials that we are studying, we have to polish and have a nice surface so that we can take it in and look at in the microscope. We polish these with these pads of paper, which are impregnated with little diamond crystals. Okay. It's also very common to have diamond used in really thin films. So it can be as hard surface coatings for cutting tools, medical devices, and things like that. Graphite is analogous to that layered structure that we just talked about. So it has strong bonds in these hexagonal arrays, and then weak bonds between the layers, these van der Waals forces that are relatively weak. And this shows up in how we tend to use this. So graphite is well used as a lubricant. So for example, if you are having trouble with your key to your house or your lab or whatever you're worried about, the first thing a locksmith will usually try is they'll do what's called they'll graphite the lock. And basically what they do is they just put some loose graphite in there, and then you stick the key in and turn it, and it breaks that up and tries to use that as a solid lubricant. So you do that so you don't have to put oil and get all this gunk inside of your system. And then the fullerenes and carbon nanotubes we talked about are just curved and warped versions of this. So if you curve those layered structures around, you can get buckyballs and carbon nanotubes. Okay, so the next thing to mention and talk about is point defects. So it turns out that point defects are a little bit more complicated in ceramics because we have to satisfy that charge neutrality. So for vacancies, we can actually get vacancies for both cations and anions. Okay, so this is showing one of those large orange anions gone or one of those small blue cations being gone. Interstitials are a bit weirder. So we can get a cation interstitial. This is where an extra blue atom has found some open space in the structure and found in there. But it's important to point out that we don't normally see interstitials from anions. So if you think about it, it'd be really hard to fit another big orange atom anywhere in this lattice because there's not enough open space. So the fact that they're generally larger means that they're not going to be able to form interstitials. So we often think of defects in ceramics because we have to balance the charge as pairs. So the first type I want to introduce is what's called a Frankel defect. So this is a cation vacancy and a cation interstitial pair. So you can think of this as this cation, which was here, has moved into an interstitial site. Okay? So on net, I still have the right number of anions and cations in my material. My charge is 0. That's all good. The cation has just moved, okay? And because of that movement, it creates two defects, a vacancy and an interstitial. We can have a different type of pair, something called a Schottky defect. And this is where if we have a vacancy of a cation, we also have vacancy of a cation, we also have a vacancy of an anion, okay? So for every negatively charged one, and we take a positively charged ion, and again, the charge is balanced out. Okay. Now, generally, we can think of these defects in the same way and with the same principles we introduced when we were introducing the concept of vacancies. So the equilibrium concentration of defects inside of the material is going to be dependent on the temperature. It's going to be proportional to an Arrhenius type of law with an activation energy and the temperature effect. So let's think a little bit about how that charge neutrality has to be balanced. And because this comes up in how we start substituting in other systems. So if we have sodium chloride, so on the left here is our starting structure. So the charge is exactly balanced out. If I were to think about replacing one of these sodium atoms with a calcium atom, I would have to recognize that the sodium is a +1 charge and the calcium is a +2. So if I replace one of these with a calcium, and that's all I do, I wouldn't have charge balance inside of my sample. I'd have an extra positive charge. Okay? So what actually tends to happen is if I have a calcium substitutional impurity, I need to have another vacancy to also help balance that out. So in this case, I'm adding this calcium 2+ ion, but I have to also remove another sodium, okay? So that the net effect is that this still has a net 0 charge. So this is a substitutional cation impurity. We can do the same thing with the negatively charged anions. So if I go with that same sodium chloride crystal structure, if I want to replace a chlorine with an oxygen, this oxygen has a -2 charge. I can replace it, but I also need to create a vacancy next door to it so that, again, the net charge is 0 inside of my sample. So we can have those same type of substitutional impurities we saw. We can have interstitials, we can have vacancies, but we have to keep in mind what the effect on the overall charge of the system is. To keep going through some of our topics that we introduced, we can also build up and look at phase diagrams for ceramics, just like we did for metals. So the first phase diagram we looked at was a fully soluble one. This was something like copper and nickel. Low temperature, fully soluble, high temperature, it was liquid. This is a plot that's actually showing the phase diagram for alumina and chromia. So aluminum oxide and chromium oxide, which behaves very similar to that copper nickel system, okay? On the far left, I can have pure aluminum oxide. I can add chromium. So those chrome atoms are replacing the aluminum atoms. And it has a solid solution that can go all the way over to when I'm fully chromia on the other side. Okay. And we actually can work with this in the same way. So if I'm in a different region, it tells me what my equilibrium phases are. And then if I'm in this liquid and solid solution, I can do the same type of calculation for my tie lines and figure out what the concentrations are. Okay. The main difference, this thing looks very similar, but if you go and reference that copper nickel phase diagram, these melting temperatures are much, much higher. We can also have the different types of eutectic and peritectic and eutectoid, all these different options of phase transitions that we mentioned before. This is showing an example for alumina, it's on the right, and magnesium oxide is on the left. So there's some solubility of alumina in magnesium oxide, but at some point you start to have a two-phase region, okay? If we move into this two-phase region, we see that it separates into a magnesium oxide solid solution. And this is something that's analogous to that intermetallic we mentioned, okay? It's not metallic, so we wouldn't call it that, but it's some ceramic compound, okay? This magnesium aluminum oxygen mixture is actually something special called spinel. And it's like that intermetallic, but it's also worth pointing out that although at low temperatures, it has a perfect sort of stoichiometric compound formula of 1 magnesium, 2 aluminum, and 4 oxygen. At high temperature, because these are higher temperature materials, you can get some solubility. It means there can be some variation in that magnesium and aluminum relative amount. But again, you can work your way into different regions of this phase diagram in the same manner. Moving on to mechanical properties. One thing we mentioned early on is that ceramic materials are more brittle than metals. And to understand this, we can consider the deformation mechanisms we talked about. So we talked about how in crystalline materials, dislocation motion is what ends up causing plastic deformation. So in these ionic solids that we've been talking about, this dislocation motion is going to be very difficult. So there's few slip systems, which is a problem. And also the resistance to motion of ions of like charge, think about moving 2 anions past each other, is going to be very difficult. Okay, so the net effect is our stress strain curves end up looking like they're linear elastic until my sample breaks. Because of that, we actually have to change how we test these materials. It's very, very uncommon for people to do compression or tensile tests, what we call uniaxial tests, where we just deform it along one axis on these brittle materials. It's much more common to use things like a 3-point bending test. So the 3-point comes about because there's 2 bottom points that the sample is rested on, and we press down with a given force and bend this piece. In this case, the bottom is being pulled in tension, the top is being compressed. And it turns out it doesn't really matter. You can have different cross sections. You can have a rectangular cross section, a circular cross section. You're really testing the same type of thing. When you're doing a test like this, usually what you're tracking is what's the force that's being applied and what's the deflection of that sample at the midpoint. So if you do a test like this, you'll get a linear curve of force versus displacement. We know that we want to sort of normalize things into stresses to be able to really put some meaning on this. And the way we usually do this is we calculate what the stress would be at that top region, which is primarily in tension. Okay? And we can account for that with just the geometry of the sample. So if we have the displacement, we can account for that by the length, and we can talk about the cross-sectional area to account for turning the force into a stress. Another thing that pops out is that these materials, these ceramics, tend to be very brittle, but also there tends to be some uncertainty or unpredictability in their strength values themselves. So if we go and we took an alumina sample and we were to test 1,000 of them, what we would find is that there would be a spread or a distribution of measurements we'd find for the strength. So this plot is showing the strength that was measured in a given test And on the y-axis is the frequency of fracture. Okay? So the way you can think about this is this peak in this curve tells you the most likely measured value. Okay, so in this case, it was something like maybe 660 or 670 megapascals. But occasionally, they measured a strength in the high 700s. And occasionally, they measured a strength in the low 400s. Okay, so there's lots of variation there. And it turns out that it just has to do with the fact that these materials, because they're very brittle, are really, really sensitive to the cracks that are sort of existing inside of any real material. So this slide is just showing a common fracture pattern, something that's called mirror mist hackle type of structure. And the idea here is that if you have a crack somewhere in your material, in this case on the bottom, it's shown on the surface, you can get this type of pattern where you have a very nice mirror region. You have this messy hackle region. And that's transitioned between the two by this mist. So you just see some smaller features there. But this is really just evidence of these cracks moving and flying through our sample very easily. So if we want to go and measure the strength for a ceramic, we would, again, do so with a bending test more often than a uniaxial test. So again, we're going to do the same type of 3-point bend test. All the geometries are the same. And again, we're going to look at that region of max tension. You can calculate what your fracture strength is for each of these two geometries. This is showing the final load at failure. Okay? And if you do a test like this, you can then extract out properties like the modulus and the failure strength of your material. Okay? Now, it's important to point out that these can be high or low. So for example, silicon nitride and silicon carbide are very, very strong materials in general. And glass, soda lime glass, is relatively weak comparably. Here we're showing another plot or another table with more data. Again, silicon nitride, zirconia, these can be very strong materials, but sometimes you can have sort of crappy glasses like fused silica, soda lime glass that aren't as strong. Because these materials are brittle, they're also very sensitive to things like porosity. So if you think about it, if I have a pore, I'm missing, so it's a big void of material. That's a place where I don't have those atomic bonds that can hold the stress. Okay? So my modulus of elasticity can be described in terms of how it changes with the volume fraction of porosity. So at 0 volume fraction, this would be the modulus of my sort of pure perfect material. In this case, it's a little bit below 400. So this is aluminum oxide. That table told us it should be 393. That's about there. On the other extreme, if you go to 100% porosity, the modulus of your material should be 0, right? So you have no material, okay? And you can put real data points on this, and it turns out that this describes it pretty well. This is just fitting it with some sort of functional form. There's no sort of first principles meaning to that. It's just showing how the modulus can change with a reasonable fit to the data. You can do something similar with the flexural strength of the material. So look at how strength goes against volume fraction porosity. This is fit with a different form of an equation. Again, there's nothing sort of fundamental here, so you don't need to worry about remembering this equation or anything like that, but this is just used to describe that data. One thing you can notice is that even within a given amount of porosity, there's some spread. So at a given value of X, there's some spread in the Y in this data. So one of the last things I want to talk about is how we process and make these things. So a side effect of having materials with very high melting points is we don't often put them in the liquid state. So in metals, we usually melt them, cast them, and nucleate out the solids from that liquid state. It's less common to do that with ceramics. So usually we do things in the solid state. A good example is how we would make something like a glass bottle, okay? So this material is put in this mold, and then there's some sort of pressing operation, and it's with compressed air, it's pushed and into that final shape. But at all of these stages, it wasn't a liquid. It was a solid, but at high enough temperature that it could be pushed and molded and formed into that shape. You can also see this in powder processing, which is really common with ceramic materials. The basic idea is you have these powders of material and you want them to end up being a fully dense shape. So what you can do is, for example, take some mold of your material, fill it with powders, press it under a given temperature, and then see and find if you have a component of your desired shape. And what you hope happens is that, for example, these 4 powder particles start to diffuse and fill in that empty space and eventually become a fully dense material. And this picture on the left is showing a real example of a intermediate step. So it's not fully done. You can see there's still some pores in the sample, but you could begin to see how some of these particles, which were completely different chunks of material before, are starting to form what looked like the same type of grain structure we saw forms when we solidify from a melt. So the final microstructure doesn't have to be all that different. It's just not going through the liquid phase. So just in summary, so these ceramics we talked about can have either ionic or covalent bonds. Usually we can figure out which one dominates by the electronegativity of the 2 elements we're putting in. The crystal structures are generally based on maintaining charge neutrality and also the cation-anion radius. But remember, we did see that in that zinc blend example, it doesn't always hold. So we need to be aware of some exceptions. For imperfections, we can see all of the same types of defects we saw before, but with the added sort of complication that we need to maintain charge neutrality. So we can get vacancies and interstitials, but sometimes they happen in these pairs that are desired to maintain that charge neutrality. We could still get impurities as substitutional and interstitial atoms, again with those caveats. And finally, for mechanical behavior, if we're doing this at room temperature, we tend to do it with these bending or flexural tests. We get linear elastic response that we can use to measure that elastic modulus. And then that fracture strength can be used to go and figure out what the strength of our material is. All right, thank you very much. And I will see you all in a Q&A session soon.